To make sure you're not overwhelmed by geodetic things, I'm going to present finite element models of earthquake cycle deformation. Next slide will be a sketch of subduction zone. Oh, it's okay. So my work focuses on the vertical elastic response to great subduction zone earthquakes. So what is the first order pattern of an earthquake cycle deformation? Okay, so when an earthquake pulls up the upper plate towards the trench, at a short time after the earthquake, the upper plate still moves towards the trench. After a long time, such as in Chile, near the trench is the fault is located move towards land, but the inland area is still moving towards trench. At the interseismic stage, all the upper plate is moved towards land. Okay, so I'm going to show you the GPS observations of earthquake cycles. Here is Sumatra. So 1 year GPS data shows all the stations are moving towards trench. So seaward motion is also observed in northeast Japan. Okay, so so all the stations are still moving seaward because ocean is this side. Okay, so in Chile, about 4 decades after the earthquake, we will see the opposing motion of the GPS stations as shown here. The coastal seaward, inland seaward. Okay. North of the rupture zone, all the stations are moving landward. This is indicates the interseismic deformation. The interseismic deformation is currently observed in Cascadia, as most of you may know. The earthquake occurred more than 300 years ago. Okay. Okay, here. So the earthquake cycle deformation seems very complicated. Seaward, landward. So we may ask, what are the processes controlling the earthquake cycle deformation? We propose 3 primary subduction zone processes. One is afterslip. It causes the upper plate moving this way. And the second is vertical elastic relaxation of the earthquake-induced stressing mantle. And the last is the locking of the fault. Here is the finite element model we used for modeling. Includes vertical elastic upper plate and the elastic slab and elastic upper plate. Next slide, I'm going to show you the central finite element mesh for Sumatra, Chile, and Cascadia. Okay, so now those are model setup. Next, I'm going to show you model results starting from Sumatra, Chile, and Cascadia. Okay, here's the test using transition and afterslip. The model did a very good job. It fits the seaward motion very well. And also for the time series of those 3 continuous GPS sites, it also did a very good job. So transient origin and afterslip is preferred in our work. Now you must ask, what if there's no transient origin, only afterslip? Okay. For afterslip only model, we can also fit the data pretty good. But the problem is we have to use a very large afterslip patch at very deep depths. Okay, so this may not be physical. What if there's no afterslip? No matter how we adjust the model parameters, there's no way to fit the near field data. So transient origin and afterslip is preferred. So it's also going to use for the other 2 margins. Here's the Chile. It's also reproduces this opposing motion very well. Okay. So for the interseismic deformation in Cascadia, this model with transient origin and afterslip also did a good job here. The Cascadia would have already gone through almost a complete earthquake cycle. For example, okay, 2 years after the earthquake, those GPS stations will move seaward. 40 years after the earthquake, there will be opposing motion just like Chile. And now it's all moving landward. Okay. So just some take-home points. Primary subduction process including afterslip, stress relaxation, and relocking of the fault. And transload and after slip is preferred in the subduction process.